All right, welcome back for part three, and let's wrap this up and talk about osmosis. Okay, so here we have osmosis, which is the diffusion of water across the membrane. And the big thing to notice here that's different is that the volumes will change, and we'll take a look at why that is, right? So here's an example on the left. So we have two solutions, A and B. And the hypotonic, right, is lower in concentration, 0.2 millimolar. Hypertonic is higher in concentration. And if there is a uh, permeable membrane that water can cross, uh, this side, right, it's the concentration needs to go up. And so since concentration is a ratio, you can increase the numerator or decrease the denominator. Well, water is the thing that can move. So if water flows out, concentration will go up. And at the same time, if water flows in to B, then it's going to have a higher solution volume and concentration will go down, right? And so water will flow from A to B, osmosis will occur until they are isotonic, and in this case, exactly in the middle at point 0.3. And so diffusion occurs from the lower concentration, hypo, to the higher concentration, hyper, until they are isotonic. Now, I'll make this point again later, but that's from the view of solutes. So if we take the view of water, however, um, which is, again, the thing that's moving, right? Here, notice more of the total solution is water. So this is actually a higher concentration of water, and this is lower concentration of water. And so once again, the thing that moves from high to low concentration. It just happens to be water in this case. So it depends on if you're thinking of it in terms of the solute, it's from low to high for osmosis, or if you're thinking of the water moving, um, it's the typical high to low that we would expect. Um, okay, so here's another illustration of osmosis. If we have um, seawater, right? If you wanted to like desalinate it, remove some of the salt from it, and we have fresh water and a permeable membrane between them, osmosis can occur, and it will flow um, from the fresh water into the seawater, right? Until they're equal concentrations as much as possible. Um, and so we didn't actually remove the salt, we've just lowered the concentration by pushing more water into it. Now, if you wanted to stop this from happening, we could apply like a piston here and push down. And actually, it would be over here, right? And not let more water flow in, right? It would just stop it. This would be called reverse osmosis, or the amount of pressure applied would have to be um, the osmotic pressure, right? And you could actually push, if you pushed even more, we could push some of the seawater water into the fresh water and actually increase the concentration. So obviously that requires energy to do, and naturally it would flow from fresh water to salt water, but we can stop it with osmotic pressure and actually have reverse osmosis. Okay, so you may have heard of that if you were trying to increase the concentration of something. That's one way, or get more fresh water. Just the water flows this way. Okay, I think I promised the definitions here of tonicity. And hypertonic solutions we now know are the more concentrated solutions. Hypotonic solutions are the more dilute solutions. And isotonic solutions are two solutions with equal concentrations. And we can use this concept and these terms to predict the direction of osmosis and also the direction of dialysis. And a new term, osmolarity, is the total concentration of all solute particles in solution. Right? So molarity is concentration of one thing. Osmolarity is the total concentration of all solute particles in a solution, and that comes into play for tonicity. Here's an interesting example of osmosis. This one's pretty cool. In red blood cells, and so water can cross this membrane and can lead to potentially big problems if its concentrations get too far off. So in A, if we have isotonic solutions, let's see, here's the cell membrane. Gray is inside the cell, blue is outside the cell, and inside the cell, right, is normal, physiological, saline, 0.9% NaCl. If we have the same concentration outside the cell, inside the cell, everything is good, right? It's isotonic and it's normal. It looks good. However, if we have a hypotonic solution outside the cell, that means it's lower concentration, right? And lower concentration outside the cell means water will flow away from that to have less volume and into the higher concentration to decrease that volume. But that's a bad thing for a cell. And so if water flows in, the cell can rupture. And we have hemolysis, right? The water flows into the cell. Now, if we have a high concentration outside, then water will flow from inside the cell out to, again, try to bring it in to balance. But then all the water is flowing out, right? And we have a shriveling cell and we have crenation. So those are both pretty bad, right? And so now you can think about why you want to give an IV solution that might have basically a baseline of normal saline in it so that you don't have hemolysis or crenation occurring. So to bring these two together, here at the top is dialysis, and at the bottom is osmosis. And again, the easiest way to tell right away is here, right? Volume change results from flow of water, which is osmosis. And the thing that flows always flows from high to low concentration. So in dialysis, the solute moves from high concentration of solute to low concentration of solute. And in osmosis, water moves from high concentration of water to low concentration of water. All right, let's take a question here. Back on the red blood cell slide, select the solution that could cause red blood cells to hemolyze, that is, to burst. Okay, without going back, let's think about this, right? So hemolysis or rupturing or bursting would be water flowing in to the cell. Now, why would water flow into the cell? Well, water could flow into the cell if the concentration inside the cell is higher than outside, right? If there's a hypotonic solution outside the cell, water will flow in to try to lower that concentration, and then that could lead to rupturing. So normal physiological saline solution would be 0.9%, and so lower or hypotonic would be 0.45%. Okay, 1.5% is hypertonic, right? That would actually cause crenation or shriveling. That would cause water to flow out of the cell. 0.9% is good. That's isotonic and everything is fine, right? This hypotonic again would be hemolysis. And then glucose. Well, glucose is important, but that's a whole other story, right? And so that's not part of this. So low hypotonic solution causes hemolysis. All right, let's look at a real world example, one that you may know or may come to know in the future, and it's hemodialysis. Right, so this is a real world example of dialysis happening um, to help perform the function of the kidneys if the kidneys themselves are not functioning properly. The kidneys can remove waste product uh, and excess water from our blood and from our bodies. And if that's not working, we can step in and help. So here, this is pretty cool. It walks through uh, basically artificial dialysis, right? And so you have your patient come in and blood is removed from the body, pumped through a tube and pumped into a dialyzer, right? Which is now, here's a zoom in of that. So the dialyzer here has blood entering in it, and it's going to have all sorts of typical blood components. It's going to have small ions, waste products such as urea, creatinine, excess water, right? All of that. And what it's going to have here is a semi-permeable membrane, the cellulose dialysis membrane, and being flushed into it will be fresh dialysate, um, which would be low concentrations of all of these particles. When a low concentration and high concentration come in touch, and solutes can move through, then the solutes will flow out of the blood, and the used dialysate, it's been filled up and wasted, full of waste, it will exit, and fresh will continue to just flow in and continue to remove and filter out waste, and then it goes back into the body. Okay. So large molecules won't pass through. Excess water will also pass through. Okay, but this is a really great and useful thing, and perfect example of dialysis. And so now you know when you encounter this, it's removing solutes by passing through a semi-permeable membrane from high concentration to low. Okay, let's look at a summary of these two and the difference. This is similar to a couple slides ago, but I really like this figure. I think this was from a previous edition of your textbook, and for some reason they took it out, but I liked it, so I kept it, and I'm giving it to you right now. So this shows the two examples. So osmosis, the thing that moves across the membrane is water, and notice again the change in volumes and the simple diffusion of water from a region of low solute concentration, which is the higher water, to high solute, which is the lower water. And then dialysis is the simple diffusion of solute from high to low concentration. Volumes do not change. All right, well, that wraps up chapter 8. So, congratulations, well done, and make sure you're checking out the homework and let me know if you have any questions. Take care.